Okay, welcome again uh, in the new session. In this session, we have to discuss some different type of homomorphism, some more examples of homomorphisms, and the properties of a homomorphism. Let us begin with the uh, homomorphism is when is called is a monomorphism. So, a homomorphism phi from G to G prime, we take G is a binary operation under a star, and G1 is a binary operation under the operation O dot O. So a homomorphism is called is a monomorphism is phi is 1 1. If we have two function is for example, if we take a this is equal to phi of n is equal to we take a 2n, z2 we take a 2z, phi of this, and this defined is a phi of n is equal to 2n for all n is the element of a z, and this is clearly I show that this is a homomorphism, and then it's saying that monomorphism means a homomorphism. This means first should be the homomorphism and also satisfy the condition of this phi is 1 1 condition. So, phi of 1 1 we take as two elements, phi of m is equal to phi of n. In this case, then phi of m is defined as 2m, and this is equal to 2n, and then we show that m is equal to n. Then clearly in this case we can say that this homomorphism is phi n to 2n is defined is a clearly is a monomorphism because it is a 1 1. So, the definition is very clear and very trivial. We can say that if a homomorphism and that homomorphism is also is a 1 1, then we can show that is a monomorphism. And now, a homomorphism phi from G to G1 is called is an epimorphism if phi is onto, and then we can show that again if we have a ontoness is satisfied, then is called is a epimorphism. So, if it is homomorphism which is 1 1 is called as a monomorphism, and if it's and phi a homomorphism which is also onto is called an epimorphism. For example, just take a this I take a clearly, then phi is a homomorphism, and also I just show that this take a z to z or no problem, and then phi is not a onto because there is a no integer n can be satisfied into this is a 2z. Okay. So, this means we can phi of n is equal to 3, you cannot find as a any, or just leave it, this no problem. So, if you cannot find an integer satisfy phi n is equal to 3, so this means in integer 3 phi n cannot be equal to 3, you cannot find any element where you can there phi of n is equal to 3. So, clearly we can say that phi is not an onto. If it is phi is not an onto, and then but phi is clearly is a 1 1. So, this means clearly we can say that this phi is not epimorphism. So, is a homomorphism, but is not onto. So, that means clearly but however phi is 1 1, I already show that phi is 1 1, and then this phi is a monomorphism, but is not an epimorphism. So, clearly is not onto means this clearly is a not an epimorphism, but this phi is a monomorphism. Okay, let us have another example. We take a this example already a set of integers from z to zn under addition modulo, and then phi of x is equal to equivalence class of this, and now you can see clearly phi of n is equal to 2 of n, phi of n is equal to 2 of n because of set of this thing, and then n cannot be equal to 2n. So, clearly you can see that in this case we can say phi is not a 1 1 because phi of x we have to define in this form, equivalence classes are there. So, this means phi of n and phi of 2n are the same, but n is not equal to 2n. So, phi is not a 1 1, but in this case you have a phi is onto, and then this means case phi is onto, you can find any element into z, and this and can be written in the form of this form. So this means if you take a in particular y is equal to x, and then you can say that phi of x is equal to in this form, and this clearly we can write into a this form. So this means this is an example where we say that if phi from z to 1z defined by this equivalent classes, and then we can say that this is not a 1 but it is onto. So this is, if not 1 means is clearly is a not monomorphism, but is a onto, so it is an epimorphism. Let us try this. We have a clearly I just take a one more example, that is G is equal to be a 1 minus 1 be multiplicative group, and phi is defined from under addition plus 2 G, and phi of defined into this phi of x is equal to 1 minus 1 if x is even, and minus 1 if x is an odd. So is an epimorphism. So this means is not a 1 and but it is a onto. Okay. So first we should try to solve that this phi from z to g is a homomorphism. So we have a different possibilities of a in this example. So first we try to solve this as a homomorphism. So we just we have different cases. We have a case 1 when we take a two elements x and y both even. We take x is even and y is even, then if it both is even, then f of x is equal to 1, f of y is equal to 1. So like this map is defined into this form. I just take a into this form. We have a x and so on. We have a x, 2x, 3x and so on like this, and you have only 1 and minus 1. This is x is, if x is odd, we have to take a odd, and then we have a this is mapping to all the odd this thing, even one map to this. If it is even is mapped this, odd is mapped to this form. So we have to this is you have a 5. So all the odds, if x is odd, then is mapping to minus 1. If it is even, then we have to map to the is equal to 1. So I just take a both x and y are even. We have to just say that when property of a evenness is saying that if you have a x and y both are even. So if you take a because the map is defined from z to g, so we take a phi of x plus y, and you know that x and x even, y is even, sum is also even. So this means this is mapping to the 1, and then you know that the 1 is the multiplicative identity of this, then 1 can be written as a 1 into 1, and if 1 come to 1 can be written as a phi of x into phi of y. So this means when both are even, then we can simply say that if another condition is if both are odd. If we have just say that case 2, when both x and y are odd, when both x and y odd, and you know that the again you take a phi of x plus y, and then x is odd, y is odd, again odd plus odd is equal to even, and that is equal to even one should be mapped into the 1, and this can be written also as a 1 into 1. This can be written as a phi of x into phi of y. So in these two cases I just take a if x1 x2 both are even, then we can say that this all phi of x1 plus x2 is even. So if it is even, then we can say that simply is equal to phi 1 can be written, 1 is a multiplicative identity. So 1 into 1 is equal to 1. So 1 can be written as a 1 into 1. So this is the same as a phi of x1 and phi of x2. So this means when both are evens are there. Now suppose we have to say that both are odd. So in this case we take a even plus odd is equal to odd and odd plus odd is equal to even, and this can be written in the form of a 1, and this 1 can be written as a -1 into -1, and is again is equal to the identity. So because 1 is the inverse of itself, and this is equal to phi of x1 into phi of x2. Now similarly we can say that when x1 is a even and x2 is a odd, and then you know that the sum of a even plus odd is equal to odd. So this means phi of x1 plus x2 can be written as a -1, and this can be written as a 1 into -1, and that is equal to, we can say that this is equal to phi of x1 because x1 is a even, phi of x2 because x2 is a odd. So this means this corresponding this and this. And now the last possibility is this, when this x1 is a odd and x2 is a even, then again you have a odd number, so phi of x1 plus x2 is equal to odd, and in this case we can say that -1, this can be written as a -1 into 1 is also as a -1, so this can be written in the form of this, and in this case this is a -1 is odd, odd 1 is equal to x1, so phi of x1, and this is equal to even, so we have to write as a phi of x2. So we discuss all the possible cases when x1 and x2 are both are odd, both are even, one of them is odd, one of them is odd, even, and then we have to show that in this case this satisfy all the properties of this homomorphism. So in general we can say that for all x and y, x1 and x2, phi of x1 plus x2 is the same as a phi of x1 and x2, but again phi is epimorphism because you know that phi of z is nothing but is equal to generated all of z, g, we have a phi of z can be nothing but is equal to whole of g. We have to all the maps is mapping to the even and odd, either mapping to 1 or either mapping to -1. So this means clearly you can say that phi is onto. So this means we have to show that this is a homomorphism and also is a onto. So this means this phi is an epimorphism, but phi is not a, clearly is not a 1 because if you have a two numbers is different, we have to giving because we have a phi of 3 is equal to -1 and phi of 5 is -1, but 3 and 5 are different. So this is clearly in this case we have to show that this is not a 1 but it is a onto. So is a epimorphism, but it is not an monomorphism. Okay, so now let's define another important concept in this homomorphism. We use the many times in the proving the our standard fundamental theorem of homomorphism, and the theorem of isomorphism is a kernel of a homomorphism. So let before properties I just define a kernel. So let phi be G to be a homomorphism, and then kernel of a homomorphism G to G1 is the set of x belongs to G, f of x is equal to E1, E1 is the identity of a G. That means we can say that if we have a like this, so I take a this is equal to G, and we take a this is equal to G1, and this is equal to we have a E1 is the identity. Now I just take a sum of the elements where here these are the elements. I take this, these are the elements. So these are the elements who these are the mapping to this form. So this is nothing but is equal to, we say that this is the kernel of this. So those elements which is mapped from G to E1, and that is the collection of this is nothing but is equal to is belong to the kernel of this set of this is equal to phi. So kernel of a phi, we simply say that denoted by KER of phi, or we can generally write is a kernel of a phi, but we have to notation this KER of a phi. For example, we have to take a map z to 2z and define in this way phi n is equal to Tn, and now clearly we show that this is equal to homomorphism. That means we can, if we find what is the kernel of this phi, kernel of a phi is saying that n is the element of a z such that f of n is equal to E1 of the identity of a this set, and identity of a this is our G and this is our G1, and the identity of a G1 is equal to 0, 0 belongs to the G1 is the additive identity. In this case, that means we can say that this is can be written as a n is the element of a Z such that f of n is equal to 0, and in this case we can say n is the element of Z such that n is defined as 2n is equal to 0. So, this means we can say that this is nothing but is equal to, you have to just say that n is equal to 0. So, means you have a only 0. So, this is clearly n is equal to 0 is the element of this thing. So, this means kernel of a phi of this set is nothing but is equal to kernel of a phi is nothing but is equal to is a only the identity element in this. So, the only identity element in this set of a G, this is Z, this is only the identity, this is you have a 2Z, so this is you have a phi, and this is some identity 0 and this identity 0. So, this means this is only the identity element which map into the this 0 and no other element which we have to map into the this 0. So, this means the kernel of a phi is nothing but is equal to we can say that this is equal to we have a identity. So, kernel of a phi is clearly is a identity in this example. Let us try to some more examples. Let Z be a group of integer under addition, and this is under addition modulo, and then we have to just say that is a phi of Zn is equal to equivalence classes of a Zn, phi of x is equal to x, x is nothing but is equal to equivalence class in the general. We have to show that, and now we have to prove that this is clearly is a homomorphism. So, if this is a homomorphism, that means we have to find the kernel, and that means kernel means we have to take some arbitrary element belong to the kernel of a phi, means we simply say, yeah, or this way like kernel of a phi is equal to, so we have x is the element of a Z such that f of x is equal to identity. And now in this case you know that this means we can write the x is the element of a Z such that f of x is equal to identity is a equivalence class of a 0, and now this is equivalence class of a 0. That means equivalence class of a 0 means x can be written as a n times of a q for some q, and should divide in the form, and then n q for some. So, this means equivalence kernel of this is nothing but is equal to all the elements where n q form, where q is the element of any integer. So, this means kernel of a phi in this case is nothing but is equal to we say that this is equal to same as a n q. Okay, so now we have a one more example that is interesting one. This means we have to just check phi from C star. C star means we have a is clearly is a non-zero. We take a C star means we can simply say that is this is nothing but is equal to, we can say that non-zero complex number, and R star is equal to, we can say that non-zero real number. And the map is defined in the form of a phi of Z is equal to absolute value of a Z. So, this means we have to now you see we have to take a Z1 is the element of a complex non-zero complex number, Z2 is the element of a non-zero complex number, that's under multiplication is group, this is ultimate multiplication is equal to Z1 Z2 is also the element of a non-zero complex number, Z1 Z2 is also the element of a non-zero complex number. Now, we have to take a phi of Z1 Z2 is equal to mod of Z1 Z2. Now, use the property of a absolute value of a Z1 Z2 in a complex number. We can say that this is simply is equal to is right in the form of a Z1, and you have a clearly this is Z1 and mod of Z1 and Z2, and then we have to phi of Z1 phi of Z2. So, this means clearly we can say that if a map phi from C star to R star is defined by absolute value of this Z for all Z is the element of a C, star, and clearly this is a homomorphism. Now we try to find the kernel, and now the kernel of this phi is can be written in the form of a some z is the element of a non-zero complex number, and then such that you have a f of sorry, this is we have to taking the phi of z is equal to, you have a identity. Now you just see this is the identity element is here is equal to 1. So this can be written as z is the element of a C star such that phi of z is equal to 1. Now this is nothing but equal to z is the element of a C star, and this is equal to mod of z is equal to 1. So this means kernel of a phi is only those elements where mod of z is equal to 1 is there. So now we can just say that into this form. This kernel of a phi we can write in the form of a phi of z is equal to 1, because under this R star multiplication identity is equal to 1. So if the 1 is multiplicative identity, then we can simply say that kernel of a phi is the same as a mod of a all z belongs to C star, where mod of a z is equal to 1. Let us try now another example. I just take let phi from R star to R star and define phi of x is equal to x to the power of 4. Now is a homomorphism, is clearly homomorphism because we take a R star to R star. So we take a x1 to the, because this is under multiplication is abelian group, and then now the property of this a b to the power n is equal to a to the power n b to the power n, and then by this property we can say that phi of x1 x2 by the map define is equal to x1 x to the power 4, and then we can say that x1 x to the power 4, and this can be written as x1 to the power 4 x to the, and then x1 to the power 4 is equal to phi of x1, x2 to the power 4 is equal to phi of x2, and then this clearly is equal to of homomorphism. Now we have to try to find the what is the kernel of this set. Now kernel of this set can be written in the form of this, we have x is the element of a R star such that psi of x is equal to phi of x is equal to identity E1 of the second group, and this can be written as x is the element of a R star, and then you have a phi of x is equal to 1, and this means you have a x is the element of a R star such that you have a x to the power 4 is equal to 1. Now you see, if x to the power 4 is equal to 1, this means x to the power 4 minus is equal to 0, and then we can say that this can be written in the form of a x square minus 1 and x square plus 1 is equal to 0. Then we have a x square minus 1 is equal to 0 and x square plus 1 is equal to 0. Whenever x square plus 1 is equal to 0, then x is equal to, you have a plus minus I. So that is not a possible, and that means we have a, because the set of we have to taking is a all the elements are a non-zero real number, but in this case we have a x square plus 1 is equal to 0, means we have x is equal to imaginary. So this case is not a possible. The only possibility thing is you have a x square, only possible thing we have a can say that x square minus 1 is equal to 0, then x square is equal to 1, then x is equal to, you have a plus minus 1. That means we can say simply that this is the nothing but is equal to 1 and minus 1. So in this case we can simply say that the kernel of this phi for this particular group we define are non-zero real number to non-zero number. Phi x is equal to x to the power 4 is nothing but the kernel is the element of a kernel is 1 and minus 1. So you can see there, we can see that in the kernel is only 1 and minus 1 are the element in this case, because we have two possibilities there. If we have a this complex is not a complex, so this is x square plus 1 is excluding because of the complex number roots are there. So this means we have only possibilities this is 1 and minus 1 are the in elements in the kernel of a phi. So this means this clearly we can say that this is x to the power 4 and this x to the power 4 means I simplify in this form x to the power 4 is equal to 1 means x to the power 4 minus 1 is equal to 0. Then this can be written as x square minus 1 and x square plus 1 is equal to 0. Now we have a possibility x square minus 1 is equal to 0 and x square plus 1 is equal to 0. This is not possible because it is a complex root. So we have a getting from this is equal to complex roots, but our set is a real. So only possibility we have a x square minus 1 is equal to 0 and this means we have a x is simply is equal to you have a 1 and minus 1. So x belongs to the you have a r to the power belong to the set of a non-zero real number. Then kernel of this phi is nothing but is equal to we have a 1 and minus 1. Now one more try to find the I take a mapping from complex number under addition to the set of real number under addition, and then phi of x plus iy I define as x only the real. Then this is clearly is a trivially is a homomorphism. We take any two element this is x1 plus iy1, x2 plus iy2 are the element of a complex, and then we have to write into this form. Now we have to taking this sum of this and elements of I together x1 plus x2 iy1 plus y2, and now because of the phi of x plus iy is defined in the x, so we can write in the this is x plus x1 plus x2, and by the again definition x1 can be written as a phi of x1 plus iy1 and phi of x2 can be written in the form of a phi of x2 plus I of y2. So by this we can simply say that we take a two element, take a different elements of this complex number, sum is this means homomorphism is mapping is preserving. So in this case we can say that these two preserving means this is clearly is a homomorphism. Now what is the kernel of this? Again kernel of we have to find. Then we have a some element of a x plus iy is the element of a C, such that you have a phi of x plus iy is equal to identity. You have a now you know that the identity x plus iy belongs to the C such that phi of x plus y is equal to you have x and additive identity is equal to 0. So this means you can simply say that all the elements is equal to x is equal to 0, then the kernel is simply that is equal to this all the imaginary part. So this means set of a imaginary number is the kernel of a this set. So we can simply say that the kernel of this set is set of all the imaginary numbers we can easily find into this form. Okay, so now I just take a one more example. This is the last example for today lecture, and in the next class we have to continue for some property. So let the mapping we have defined for under addition to under non-zero set of real number under addition to set of a non-zero real number under multiplication ix, and now this is clearly homomorphism because we take any two elements of a r. This is clearly so any two elements of r, x and y is the element x1 x2 are the element of a r. If we take x1 and x2 are the element of a r, then phi of x1 plus phi of x2 exponential of I of x1 plus I x2, and this can be written as a I on x1, and then this can be written as a phi of x1 x2 is equal to clearly is a homomorphism. Now this is under non-zero real number, then identity of this set is equal to under multiplication is a 1. So, kernel of a phi x is the element of a set of a real number, phi of x is equal to identity element is equal to 1, then exponential of e to power x is equal to, so this is exponential, this is not a power, this is written as a exponential of a, this is e to the power ix or exp ix, this is in this form. This is not a power, this is in the bracket is the same. So, if we take a exponential of ix is equal to 1, then this is a cos x plus I sin x is equal to 1, and then this is the only value where cos x plus I sin x is equal to 1, means we can say simply z is equal to this for all m 2m pi z, because we have to getting this value 1 for 2 or always. This means the kernel of a phi is equal to 0 plus minus 2 pi plus minus 4 pi, all this thing. So, in this case, this map defined from set of a real number to the set of a non-zero real number under, this is under addition and the g1 is under multiplication, and we define as a phi x is equal to e to the power x or exponential of x, not a, this is not a power, this is clearly written as a exponential of ix, or we can say that e to power x, this is a e to power. So, this is simply e to power x, this is not expression. So, we can simply say that clearly this map is defined as a homomorphism, and also kernel of a phi satisfy this is nothing but the kernel of a phi is equal to, you have a 0 plus minus 2 pi plus minus 4 pi. So, this is we have to, and so on like this. This is so we can say this is into this form we have to write. So, these are the kernel of this phi. I think I have to stop today's lecture here, and then we have to discuss some this kernel and monomorphism, epimorphism, and kernel of homomorphism. So, in the next class, I continue to the some properties of this homomorphism. So, thank you very much.